Hello, Peter. How are
Hi,
you?
I'm good, thanks. Nice to meet you.
Nice to meet you, and welcome to BuzzConf 2020. We have our audience out there on YouTube. Remember that everyone can ask questions by the end of the talk. And so our keynote speaker, who will be closing the event, will talk about what, not where. Why a Blue Sky OS, which is a very intriguing title. His specialty is distributed systems. And so we're so excited to have you. You're welcome to share your screen whenever you're ready.
Thank you so much. Just give me a minute to figure out how to do this. Can you confirm to me that you can see my screen with the title of the talk now?
Yes.
Wonderful. So I'll begin. Thank you so much. Thanks for tuning in, everybody. I'm incredibly delighted to be here. My only regret is that I couldn't be in Buenos Aires today. My name is Peter Alvaro, and this talk is called What, Not Where. Why a Blue Sky operating system? And I'm glad you think the title is intriguing. Instead of trying to unpack it right now, I'm just going to leave it there. And my hope is that the audience, it'll begin to dawn on the audience what it means, starting about halfway through the talk. I'm a professor of computer science at UC Santa Cruz, where I lead the Disorderly Labs research group. I joined the faculty at Santa Cruz in 2015. And I'm really excited about this talk for a couple of reasons. One of the reasons is that for the first 4 years of my time at Santa Cruz, my lab and I were principally focused not on building things, but on tearing them down. We work in bug finding. So we take systems and try to shake them loose. And so it's really exciting for the first time in a long time since my PhD work to be talking about a constructive result, something that we built as opposed to broke. And this talk is also secretly, well, not even that secretly, an advertisement for university research. Universities are pretty much the only places on Earth on which you could take on a project so sort of crazy, taking 5 years to go build a new operating system for some reason. I always try, when I go out and give large talks, to recruit new students, because it takes a village to build systems. And it's not lost on me that I couldn't have picked a worse time in the history of my country or in the history of the University of California to try to recruit international students. Like, the reality in America and in the UC is somewhat ugly right now. I can see that. But here I am asking you anyway. Consider taking a chance on PhD research. I hope today to paint a picture of the absolutely wild, audacious, and maybe most importantly, transformative work that a PhD gives you the unique opportunity to do. So today I'm going to talk about a new operating system called Twizzler. On the surface, Twizzler is an operating system explicitly designed for a future of persistent, byte-addressable memory. So memory that lasts forever, but which we can compute directly on, like RAM. But more fundamentally than that, than being like a reaction to a new tech, Twizzler is an embodiment of a new kind of operating system, a data-centric operating system in which information, rather than the ephemeral actors like processes and computers that happen to behave against it, is the primary citizen of the world. We believe, I certainly believe, as controversial as this may sound, that Twizzler finally realizes the true vision of Unix in a world of long-lived data. I'm going to argue in this talk that data centrism was always the right design, but that some recent technological advances make this the right time to realize the dream, that we'll be leaving too much on the table if we don't do something disruptive to the stack, like now. Another thing that I'm really excited about is that for the first time, I'm presenting work not directly undertaken by myself, but by a student who I mentor. This is Daniel Bittman. He's a 5th-year PhD student at UC Santa Cruz, and he dreamed up and then built the operating system that I will be describing today. I still remember when I was a PhD student seeing my advisor get up on stage and boast about my work, and I just can't tell you how proud I am to pay that forward. So let's talk about the state of the art for a minute, right? As you would expect in a talk about a bold new technology that isn't quite ready yet, before I start overclaiming, I have to first talk about the current state of the art and kind of pee on it from a great height, so to speak. So I'll begin with this like rhetorical question. What are computers for anyway? I don't think it's that controversial for me to assert that the main job of computers is storing, processing, and ultimately sharing information, data, right? Not so much finding giant primes, although that's important sometimes. It's mostly custodianship of information. But in the current state of the art, if you want to get at information, you got to go through one of these guys, an agent. And I could be talking about a process, or I could zoom up and be talking about a host, or zoom down and talk about a thread, but an encapsulation of computational behaviors. These things are the first-class citizens of modern operating systems, right? If we think of an operating system as a world, that world is peopled by processes. Oh, look, there are some now, engaging in behaviors. Processes, agents, are self-centered, solipsistic things. They believe, or they prefer to believe, that they're the only processes in the world. And whenever anything is shared, like data, they kind of assume the worst regarding the kinds of conflicts that could happen. Sharing's awkward in general. If processes want to share information, they either need to use an external mechanism, such as the file system, in which case they need to agree upon a name for a file, and agree upon its layout, and agree upon the order in which they will access it. Or if the data is locked up in one of their private memories, it's even trickier. They need to name each other and agree upon a protocol to move the data. Data is secondary to processes. Let's zoom in on these funny guys. What exactly is a process, after all? Well, it's an abstraction provided by Unix-like operating systems that couples together a couple different concerns, right? Fundamentally, a process is, maybe most importantly, a collection of threads of computation. And in our current models of computation, it's hard to imagine doing stuff without threads of control. So a process is a collection of threads, and that seems fundamental. But a process is also a collection of pieces of context or metadata that it schleps, it carries around with it, that are required to unlock, access, and manipulate data. Let me explain what I mean. By context, I mean a process carries around with it its own virtual memory, an isolated memory region in which it's permitted to point to other memory, provided those pointers don't cross outside of its private memory. A pointer is only meaningful to the owner process. But that's not all. A process also carries around a bunch of kernel state, a bunch of integers like file descriptors and sockets and so forth that it uses sort of as tokens to enlist the help of the kernel to perform inter-process communication or to perform I/O. And it also carries around with it some security context, right? So a process is both an abstraction of compute and also context for data. So let's ask another rhetorical question. What is the job of a process? What are processes actually for? To answer this question, I'm inclined to look at a day in the life of a process. And since I did my PhD in databases, when I think about low-level, data-intensive programming, I tend to think about implementations of database internals, joins and external sorts and grouping and buffering and so on. So the next few slides I'm going to show you are all drawn from this famous Ramakrishnan and Gurkha cow book. If any of you took databases in undergrad in the last 20 years, it's very likely that this was your text. And these are all figures from this book. I don't want you to look too closely at these figures because they're going to go fast. But what I want you to focus on is the overall shape. So here we have a figure describing external merge sort. And what we see happening on the left is a representation of blocks on a disk. So on the left is the input file. And we're writing out multiple sorted runs. So what we see on the right is multiple output files. So there's cold storage on the left and cold storage on the right. And what we see in the middle, those four little blocks, represent buffers of main memory, DRAM, that we can compute directly on. So what's happening is, and in fact, this is going to be true in all these pictures. Here's another picture, double buffering, hash joins. In every case, we have cold data. And then periodically, this long-lived data needs to be transformed in some way. So it's sort of vacuumed through this bottleneck, through the von Neumann bottleneck, so to speak, into a very small main memory. Remember, we assume we have a few pages of fast memory that we can compute directly on and essentially infinite cold storage, right? And I spend compute resources and I spend developer time ferrying data between these exclusive, persistent, and computable domains. And that is the better part of what systems programming is. There's 4 pictures. The sad thing about this is they all describe completely different algorithms, but they all look the same. To see the difference, you have to squint into the fine print in the middle. That's where the important stuff is happening. And the rest of it is just data motion, data movement. Let me tell the same story in a slightly different way. Many of you who took systems classes will be familiar with the memory hierarchy. This was a scribble that I did in the spring when I was teaching a systems programming class. We represent the diverse storage media that we have access to in a typical computer as a pyramid, where as you go down the pyramid, you have more abundant memory because it's cheaper, but it's also slower, with magnetic tape being the slowest and cheapest, spinning disks being faster and more expensive and less abundant. And as you zoom all the way up to the top, you have your SRAM and ultimately your registers that you only have like a dozen of them, but they're super fast. Sometimes, data certainly moves throughout this hierarchy when we do computing. It needs to move to the top so the CPU can access it. It needs to move down so that it can last beyond reboots. Sometimes that movement is transparent and handled by the system. But there's one important kind of movement across this barrier that I've drawn. When data is supposed to be moved from the volatile domain that will go away on a restart to the persistent domain, as you just saw, the programmers have to get involved. A big part of systems programming is being a ferryman on this river of the memory hierarchy. And just to really reemphasize this point, let me make it a third way with pictures I stole from Daniel Bittman and his ATC talk earlier this month. You have some data that is persistent, that is written in a representation in a format appropriate to cold storage on a block device like a disk. And if you want to compute on it, you have to spawn a process. And that process enlists the assistance of the kernel to issue a system call to read that data from the disk and move it across the persistence boundary into volatile memory so that we can operate on it with loads and stores. Then often, although as my advisor yelled at me on Twitter, not always, the programmer then needs to spend additional compute cycles converting that data from a representation appropriate to block-oriented storage to a representation appropriate to fast in-memory computing, like turning it into a pointer-heavy data structure like a tree or a DAG that involves swizzling pointers that were written out to disk. And then, magic happens. You do your algorithm, but then when you want the data to last beyond the lifetime of the process, you convert it back to a disk representation, and then you enlist the help of the kernel again and issue a write system call. And now you've done all your sort of stations of the cross. You've got this cycle. But I would argue that it is not a virtuous cycle. It is a vicious cycle because all the stations of the cross are identical. And the place where the interesting algorithm happens is just a speck on the graph. Like, this is what systems programming looks like today. And over there in the lower left-hand corner, that could be us in a data-centric world where we could focus on computation rather than data movement. And just to pee on the state of the art a tiny bit more before I move on. When the data isn't in a file system external to processes, but is ensconced in the virtual private memory of a process, sharing is even more awkward. As I briefly indicated before, now, when a process wants to share some information, it needs to name not the information, but some other process who's the recipient, or some indirection like a named pipe or a socket. Then the two endpoints need to agree upon a protocol. And ultimately, the data, which, as I argued, it's the long-lived thing, it's the real thing, it's the reason the processes are there in the first place, becomes an ephemerum that travels in a short-lived message after having been marshaled into it between the processes, moving from the private virtual memory of the one to the private virtual memory of the next. And I'm belaboring the point because it matters. There's something not just fussy and awkward about this, there's something backwards about this. The idea that processes are like these long-lived things that have names, right? And that exhibit behaviors. And data is just this flash in the pan, right? Doesn't it seem weird that behavior should have a name and have a long lifetime, but data is treated as an event? It's not just wrong. It's upside down somehow. Anyway, and it seemed like systems programming might just go on looking like that forever, when suddenly a wild new technology appeared, memory, that fits right in the DIMM slot. Memory that we can compute directly on using loads and stores in a manner indistinguishable from if it was RAM. Memory that's persistent. If I do a store to it, I can do a load after a reboot. Memory that's close in speed to RAM and getting closer. That's cheaper than RAM and getting cheaper. Memory that you can buy from Intel today. So like, holy crap, you know, like what should we do with this stuff? Well, when a new technology comes along that changes our assumptions about system balance, we're faced with some choices. And typically there's one, you make one of two choices, right? You take an incremental approach to the problem. You play it safe. You figure out the smallest change that could be made to our existing model of computer systems that will accommodate and hopefully like exploit the new technology, and you make it, right? Or you do blue sky research, or what some people call green field research, or what some of my more skeptical colleagues call boil the ocean research, where instead you say, no, 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 we're going to rethink the whole system stack with the explicit goal of taking the best advantage of the new technology, exploiting it to the utmost. Needless to say, incremental work, at least on the surface, is safe. Blue sky work is fun. If we shoot for the sky, we might never reach the future that we predicted, and then we throw away the work, which is sad. But like if we increment, we're not going to take the best advantage of the technology. We're probably not going to have any fun. And worst of all, we might get scooped. Like incremental work isn't necessarily safe work because often doing incremental work is doing the obvious thing. And what makes you think you're the only person doing the obvious thing? If you're not, and you're not the first to publish, you have to throw that work away too. I like to say to my grad students, we never have to worry about getting scooped because we're working on stuff that's so outlandish, nobody else would even try it. And that's a nice position, in my opinion, to be in. Let me illustrate this point about incremental versus blue sky in the context of another solid state technology that made a big splash 15, 20 years ago. We all remember SSDs, right? They came around and they became affordable pretty quickly, surprisingly quickly. And man, they were going to change everything, right? They were just going to totally upset our models of storage because they sure look different from spinning disks, right? These characteristics are not the characteristics that we've for 30 years have come accustomed to with mechanical disks. We can, with an SSD, issue blazing fast random reads to any location. We don't need to worry about disks spinning and arms and things like this, right? And we can issue them in parallel, which means we can pack these things onto our machine. And if we have enough parallelism, we can exploit more bandwidth. So that doesn't look like disks. You also can get blazing fast write throughput on SSDs, provided you write to new places, provided you don't try to update the same place. And this gets us down to the real Achilles heel of SSDs, which is their write endurance and their lifetime. As many of you, I think, are aware, you can't erase individual pages in an SSD. You have to erase whole regions, and each region only has so many write erase cycles before it wears out. So if you have a logical hotspot in your data, you have to get very creative about how you spread those writes around the medium. So, these characteristics look different enough that it's tempting to say, let's invent a new storage interface, not, for example, POSIX, that is tailored to the best characteristics of the media. And the Corfu folks, I don't know how many of you are familiar with Corfu, it's like an academic research infrastructure storage system, had exactly that idea. They said, well, let's not try to make these things look like disks because they aren't like disks. Instead, let's attach raw flash devices to a high-speed network fabric. And let's have the clients participate in a fairly natural append-only, totally ordered log abstraction akin to the way that Kafka works. This log abstraction, it turns out, is expressive enough to be able to build up consensus and concurrency control and hence arbitrary storage or database systems atop it. It's a very powerful infrastructure for systems building. What are the high points? Well, Corfu offers arbitrary parallel read bandwidth. If you want more bandwidth for your reads, all you have to do is attach more flash devices. That's amazing. Corfu also offers non-interfering writes that we can write out as fast as we can get positions in the log. So a sequencer says, you're number 47, you're number 48, you're number 49, and we can all write in parallel to independent regions of the fabric. So it's like, it's perfect. It's a brilliant design. It exploits the best features of the tech. Overwriting's hard? OK, we won't do it. Oh, reading in parallel is easy? Let's do all our reads in parallel. Let's delegate arbitration to a sequencer. It's just gorgeous. What's the downside? Well, it isn't POSIX. Like, what if I want to seek to some arbitrary location and do a write there? It doesn't support that. The interface doesn't support that. I mean, that doesn't bother me, but it certainly bothered a lot of people. And do you think we all build systems on top of Corfu now? No, somebody was like, can't you make these things look more like a disk? Can't I just use POSIX? Can't you just kind of cram it into our existing models? And of course, you can, right? Sometimes when a new storage technology comes along, you view the memory hierarchy not as a river, but as a bookshelf, and you just kind of squeeze in a new book. So where would SSDs go? Well, they would go there, right? They go below the dark line because they're persistent and not directly computable. But clearly, they go above spinning disks because they're faster and more expensive, right? So it's like, so what would it take to just kind of fit SSDs into our existing model with minimal disruption? And it turns out it's gonna take a bunch of work because of that lifetime issue, right? If we have a logical hotspot, we have to make sure it doesn't translate to a physical hotspot. So what we do is we create a massively complicated controller for SSDs that includes this flash translation layer, which essentially, waving my hands and mumbling a little bit, is the moral equivalent of a log-structured file system in the controller, complete with a buffer cache to absorb bursts and garbage collection mechanisms. So a whole ass file system, essentially, in the controller. And then you plug the controller into your computer, and you have a raw device. And what do you put on that? You put like ext3 on that. And now it's kind of like a disk, I guess, that's a little faster, but doesn't last as long. But we're at 3 levels of inception. And in some sense, we've squandered something, right? When you play it safe and you take the incremental route and you refuse to change how you do things, something is squandered. Something's hidden away, possibly never to be seen again. OK, so let's take a good hard look at byte-addressable non-volatile memory. Let's look at the characteristics of this new tech to help understand why I strongly think we can't make the same mistake. In this case, as I said, it looks like a DIM. It's directly computable. Its speed is within spitting distance of main memory. I can issue direct load and store instructions that return in under 300 nanoseconds. Contrast that with the microsecond that it's going to cost me merely to cross over into the kernel. Just the overhead of the context switch to enlist the help of the kernel to do I/O is going to cost me a microsecond. Now, I was more than willing to pay that microsecond to have the kernel help me out with I/O when I was going out to a disk where I was looking at 5 to 10 milliseconds to come back from the disk, right? Disks were dog slow, and there was plenty of time to do deserialization and kernel crossings while you waited for the ARM to rotate. You know, as Jim Gray might say, if I knew you were going to Sacramento to pick up a book, Sacramento is a city that is like 100 miles away from San Francisco for what it's worth. If I knew you were going to Sacramento to pick up a book, I might say to you, hey, why don't you pick me up a 6-pack at the corner store on the way? What's the big deal if you're going all the way to Sacramento, right? You can easily stop at the corner store. But if you're reaching for a book that's like on your night table, what kind of asshole would I be if I asked you to like on the way, go pick me up a 6-pack? So what's the takeaway? Well, the obvious and maybe conservative takeaway here is that the kernel has to get completely out of the way. The kernel has no place on the persistence path. That's like going to the corner store on my way to pick up a book on my table. But even that is conservative. That's not disruptive enough. Because if we did that, we still might, like, let's say we wanted to do something incremental with this new technology. What would we do? We would attempt to do the same thing we did with SSDs. We would find a place in the bookshelf where it goes, and we would fit it in. And I think it's pretty obvious that we would fit it in right on that boundary line, right? Because from above, it looks like DRAM in that you can operate on individual words using load and store, but like SSDs, its contents persist across reboots. However, I am a teacher at a university, and I have grad students who want to ask and answer really big questions. We want to do something wild. So we want to boil the ocean. We want to do blue sky research. And what's more, it's the right thing to do, because the no-brainer is the kernel has to get off the persistence path. That's obvious. But a little more subtle, if you really ruminate on these changes for a minute, is the following. Data, like if we compute directly on persistent memory, that means that data has arbitrary lifetime. Data lasts forever, by definition, because it's going to outlast the lifetime of the process that created it, right? Because if I turn off my computer, turn it on again, the data's still there, the process is gone, and of any processes that might modify it. So in the limit, data lasts forever, and processes kind of go to zero. Processes maybe just happen for a sec. Oh, that's kind of crazy, right? Well, if data lasts forever, and as I just said, it does by definition, because we're directly computing on persistent memory, then we need some mechanism for constructing long-term data references, right? We want to operate with pointers. It's an easy way to program. It doesn't make sense to put virtual memory pointers into the memory at all, because as soon as that process goes away, the pointer doesn't make any sense anymore, right? So we need some way to rethink what a pointer is and turn it into something that invariantly and explicitly refers to long-lived data. Pointers have to have the same lifetime as the data they reference. And this is a disruptive change, right? Where should the context needed to interpret data go? We've already kind of agreed it doesn't belong with the process, because the process is just a flash in the pan. Well, it should go with the data, right? And this kind of leads us to, if you accept these two sort of credos, you're already one of us. You're a data-centric OS idealist. And this is sort of a whole new kind of OS, as I said, one that centers information as a first-class concern and that relegates behavior, processes, agents to a secondary role. And it sort of goes without saying that this also comes with a new programming model that is fundamentally data-centric, that involves following the data. Twizzler is just an operating system. It's a point in this design space, providing mechanisms for applications to directly access persistent data using invariant references. Defund the kernel. Move it out of the way. Now, this is a little wild, but here is a tweet from over a year ago when we were first starting to think about the ramifications of Twizzler's object model, in particular as they refer to distribution and sharing. And I had this aha moment where I was like, well, so like as I showed you before, in the current state of the art, which is process-centric, processes are around for a long time. And when they want to communicate, they marshal some data into an ephemeral message. Data goes in messages. And as I argued a moment ago, that's somewhat backwards. In the Twizzler model, data is the principal citizen of the operating system. Data is organized into objects that have explicit identity, and data can talk about other data. But every now and then, obviously, data needs to be transformed and moved and shared. Well, this is where threads of control come in. A process may come into existence for a little bit of time and move data from one representation or one place to another, and then go away. Viewed in this way as sort of a Lamport diagram, what Twizzler has done is completely upended the model. In the Twizzler model, in some crazy sense, processes are the messages, are the events, and data are the people. Which means, when you think about it for a minute, we can probably, along with the kernel, the process abstraction should probably get out of the way too. Like, it had a good run, but we don't need it anymore, right? Once you've accepted the fact that the context required to access data should go with the data so that the data has the same meaning anywhere, then what the heck do you need a process for? A process was just a coupling of that with, oh, right, threads of communication, which I think we still need. So Twizzler has threads of communication, but it frees them from the mortal coil of the process. OK, let's get down to some technical details. Let's talk for a little bit about how memory, both volatile and persistent, is structured and manipulated in the Twizzler operating system. So an object, I don't mean anything fancy by an object. I don't mean anything OO related. I just mean an explicitly named flat region of contiguous memory that's intended to contain semantically related data. Whether, as I said, an object is volatile, stored in DRAM, or persistent, stored in NVRAM, it looks the same to the programmer. You just program it as if it were memory. Objects are also the unit of access control. So we associate permissions that resemble Unix permissions with objects and not with pages within the objects. An object can have an internal reference, as you see here, that looks like a virtual memory reference. I have a region of memory and I can point to another place in it, but just as naturally and easily, an object can have a so-called external or cross-object reference, referring to a place in another object. And the programming model of Twizzler, as you'll see, is completely built and supported by this capability. Objects are identified by 128-bit IDs. An ID space, we believe, that will be large enough for all the objects anyone will ever need, anywhere, not just on one computer. Now, so as a consequence of that, though, a logical pointer is 128 bits identify an object, and then an offset on the end identifies a page in the object. Of course, if we made these the physical pointers, they'd be awfully big, creating severe overheads and compatibility issues. So we play a classic OS trick. We create a level of indirection. Every object has a special data structure called a foreign object table, or FOT, at a well-defined location. Within an object, pointers, both internal and external, are physically represented not as object ID comma offset, but as an integer index into the FOT followed by an offset. In this way, we can maintain standard 64-bit pointers. Let's take a look at what dereference actually looks like. Over on the left, we have an object O that some process, or some thread rather, is computing on, and it encounters a reference, a pointer. It looks at that pointer. Now we're looking in the upper right. And it says, well, instead of having an object ID, it says, whatever the object ID is in slot 1 at this offset is the memory region I'm pointing to. So we go to the foreign object table and say, oh, slot 1 is 128-bit object ID A. We find that object, fault it in if necessary, and then apply the offset. The FOT allows us to store additional pieces of metadata that can be helpful too. As you see here, we've stored some protection information there. We could also store reference counts. Maybe most compelling is that we have the option to, instead of storing object IDs, we could store human readable names and then delegate resolution till the last minute. This gives us two nice features that are sort of simplicity features in Twizzler rather. The first is that we don't need an external file system. Twizzler has no file system. You don't need a file system to enjoy the benefits of human readable naming and resolution. You can get that out of the core pointer mechanism of the OS. And by the same token, this enables us to do late binding, which would have been really tricky otherwise, right? I can have an entry in my FOT that points to the latest version of libc, and I can sort of resolve it at the last possible minute, which is a capability where we become accustomed to in Unix-like systems. Now, I don't want to talk too much about the consequences yet, because I want to make a big deal about them at the end, but now's a good point to stop for a second and say, what does this all mean? And in particular, though I'm not talking about distribution yet, I'm going to make the point in this talk that Twizzler, while not designed to be a distributed operating system, made some design choices that make distribution a real possibility at a really exciting scale. So the first point to make is that in Twizzler, the fundamental change is that the idea of referring to data has changed. We refer to data based on its fundamental identity rather than its ephemeral location. We don't say the data is at this place in memory. We don't say the data is available on this host, for example. We say the data is this data. What, not where. Okay? Because the FOT is an object local data structure rather than a global one, that means that objects are self-contained. That means that objects carry around with them, as in the bad old days a process did, all of the context required to interpret, manipulate, or process the data. You never need to change the pointers, because the pointers always mean the same thing no matter when you read them and no matter where you read them. Combine this with our 128-bit galactic object space. And this means that even if we were running Twizzler on a great many computers spread out around the world, these computers would never need to coordinate on the address space. The odds of a collision are vanishingly small. And when I move an object local, I don't need to do a fix-up operation. I don't need to unswizzle anything. Those pointers mean the same thing on my computer that they did on your computer a year ago. That has profound consequences for potential distributed and disaggregated operating systems. Okay, and then before I close on Twitter and start getting really crazy, I want to talk about compatibility, right? Because if you want people to use your shiny new operating system, you do need a compatibility story. You have to be able to port legacy applications, but it's a really important part of our philosophy that Twizzler is for new applications first. Our first goal is to enable a radically simplified programming model for new applications that want to take advantage of the technology. For those applications, as you see at the top, they can directly access memory without any involvement of the kernel at all. When they need support, they get support from the standard library libtwz, which is a user space operating system, like a libOS. The kernel in Twizzler is a tiny thing called out to infrequently for management. libtwz calls into the kernel to manage physical resources for assistance and synchronization among threads. What else? And for multiplexing memory into objects. The kernel, for example, will handle things like page faults, but almost everything else is handled in user space. Our second goal, after having gotten that all out of the way, is to support legacy applications with a minimum of pain. To do that, we compiled the musl C library onto Twizzler, substituting its system calls for library calls to a Linux emulation library called Twix. So if you issue your reads and writes and you think you're talking to the kernel, we're actually proxying them through our Linux syscall emulation library right into the direct, to the byte-addressable non-volatile memory as well. We did build this system. I'm going to share the URL at the end, and I encourage you all to download it and build it and try kicking the tires. And by kicking the tires, I mean writing some new apps. But as a case study, we wrote some new apps. And we wanted to measure the two goals in that order. We wanted to show that it was easy to build new classes of data-intensive apps using the new programming model. And we wanted to show that it was easy to extend them. And then we wanted to show that it wasn't that painful to take an existing data-intensive system, in this case SQLite, and port it over. So I'm going to go through this fast because I'm less excited about graphs than I am about the vision, right? But I want to make it real for you all. So we built a key value store. And as I said, we were focused not just on programmability, how easy is it to build, but how easy is it to evolve and extend, right? So if you were doing this the old way, you'd probably have a memory map file and you got your script string block and you packed, here's your index data, here's your other data. And you kind of need to agree ahead of time about the layout. And if you change the layout, everybody who reads the file needs to figure it out. In our design, because of cross-object pointers, it was just too easy. We could kind of write the index object with all the keys, write the data object, and then essentially have the index object point into the data object in a very natural way. We don't have to pack a file, binary pack a file anymore, when you can point across objects trivially. Another nice feature of this is that when you do a get, if your data is in persistent memory, it would be a pain. It wouldn't be right to make a copy into virtual memory and then give you a pointer to the virtual memory. It'd be much cooler to return a pointer to the data on the persistent memory. And that's exactly what our KVS does. It returns a direct pointer. And then, as often happens with applications, it occurred to us after the fact, like, gee whiz, it would be nice to have access control. It would be nice to have a classified data object as well as a public one with minimal changes to our system. Now, if we were doing this in Unix, the old way, probably what you would need to do, maybe I'm not being creative here, is throw away the library KVS and replace it with a service-based KVS. And then in that service, when people sort of sign on, you can redundantly implement users and roles and permissions redundant with the OS and blah, blah, blah. It was a lot of work, so we didn't do it. But on the Twizzler port, it was trivially easy to do. Because all we had to do was create another data object with different permissions and have the index point into both. Should a user come along who doesn't have the privilege to read the lower data object, they won't be able to dereference the pointer. So this is just an evolutionary slam dunk that we were able to transparently take advantage of the operating system's built-in security model at the application level. It just so rarely happens. And then I'll go fast. The next evolution was a secondary index. Maybe I don't want to look things up by key. Maybe I want to look things up by something in the value field. And that was trivial too, because we just create another index with pointers into the same data files. The only point to take away here is that we implemented a KVS with similar features, except for access control, in Linux using POSIX calls. The code was much more complicated, obviously. Even without the access control code, it was about 40% larger, the Unix implementation, in large part because we had to manually construct and compute our pointers. We had to process file system paths in the index. We had to open, map, and grow mmapped files, and so on and so forth. And more complexity led to more bugs and longer development time. Right? So the programming model is nice. Then, let me look how I'm doing for time. No, not that great. So I'll go fast.
No problem. Take all the time you want.
OK, I'll just go at my pace. Thank you. So we took SQLite, which is something I think you're all familiar with, single node persistent SQL database. And as you may know, below the top half, the storage engine is strictly B-tree over a standard, over a POSIX. We became interested in our efforts to port SQLite in an existing port called SQL Lightning, in which the SQLite top half, the query processor and stuff, is snapped on top of the Lightning memory mapped database, which uses memory mapped files to hand out pointers to persistent data. So it's a little bit of a data-centric take given the current system stack. We went ahead and on top of Twizzler, as I showed you, we built a key value store. We also built a red-black tree implementation. And then we peeled off the API skin of LMDB and put it on top of our Twizzler implementations of these tree-based data structures, allowing us to transplant the SQLite top half without modification. So it's really SQLite with a different storage backend that happens to be running on a different operating system altogether. And then to have a little bit of an apples to apples comparison, we took that LMDB skin and put it on top of custom data structures that we wrote in the persistent memory development kit. I don't have time to talk about this in this talk, but the PMDK is very much like a library answer to the problem that we chose an OS answer to. Right? It's a more incremental and less aggressive reaction. But we felt like it's kind of the state of the art of using byte-addressable non-volatile memory without throwing away your system stack. And the point to take away here is we didn't even set out to outperform these other systems. We just wanted to demonstrate comparable performance with a simplified model. But instead, due in large part to significantly simplified code paths, we outperform all three of the other implementations, both under a read and write heavy workload generated by the Yahoo Cloud Service benchmark. So it's a benchmark workload over on the left. We're measuring transactional throughput normalized, so higher is better. Twizzler experiences higher throughput for all six of the YCSB benchmarks. Once the data was loaded, we also wanted to measure analytics workloads, right? When you load data into a database, you probably issue a whole bunch of queries. What's the median? Build an index, probe the index, these kinds of operations, excuse me. And we were delighted to find, and here we're measuring latency, right? How long normalized it takes for the query to return. So lower is better. And again, we outperform the competition surprisingly in every case. OK, enough of graphs. Twizzler was designed for the near future, a future that's right around the corner as we start buying these DIMMs. But what about the far future? Let's peer into the crystal ball for a minute. Now, take this with a grain of salt, right? Because I don't actually have a crystal ball. I can't actually see the future. The things I say may not be true. I'm just going to talk about some things that might happen, some trends that are weird and worrisome and exciting. So you remember the memory hierarchy. And for a long time, it seemed like as new storage technologies got invented, the memory hierarchy only got fatter. We just found ways to slot them in, and we found a way to make it transparent. But recent trends may be pointing to a convergence of the storage hierarchy. And I don't mean to say that we're going to throw out all the other media, but the storage hierarchy may be much smaller and may be mostly populated with disaggregated persistent memory, with caches on top, of course, and maybe some very slow storage below for stuff that you don't want to go back and look at for a long time. But storage may be converging. That's crazy. And even more worrisome, but arguably less controversial of a statement about the future, compute, for sure, is diverging, right? The way I was taught to think about computers, CPU is this massive uniform resource, and it's the crown jewel of the memory hierarchy. It sits at the top of the pyramid, and we move data up to it to compute fast, and we move it down when we want to save it for a while. But Moore's law slowed down. Dennard's scaling slowed down, right? And without the promise of this single god CPU getting faster all the time, we're forced to look elsewhere. We now have to figure out how to make our computation run on many cores. Well, wait, that was 10 years ago. Nowadays, it's like we need to figure out a way to make our computation run on that little core that's on my NIC, and those little cores that are on my smart disk maybe, and also my GPU. And also maybe I've got an FPGA board in there, because compute is heterogeneous, diverse, and increasingly distributed. And if you want your program to run fast, you need to figure out a way to spread it among the compute. Let me say something even more kind of crazy. When I was learning parallel programming 10, 15 years ago, the really hard thing was data placement and partitioning. Chopping up your data and putting it in the right places so that your extremely fast processors can run on it with like a minimum of communication or whatever. And we still have to do that. But in the future, we're probably gonna have to do something much harder than that, which is partitioning and placing not just the data, but the program. Right? We're going to have to get really creative to say, how do I cut up my program into pieces and farm it out to these distant compute resources to maximize my utilization of in the system and increase my performance? That's crazy, right? And so where's this leading? Well, look at what we have in hand. If we're really going towards this world of like total disaggregation, which it seems like we may be, what does Twizzler have? Well, Twizzler has a galactic object space with invariant pointers that mean the same thing, irrespective of time and space, okay? It has a built-in system-level notion of explicit identity that I'm about to freak out about. Data objects may point explicitly to any other data object anywhere in the world. So what does this mean in the large? Well, it seems to lead to a vision of utter disaggregation for sure, but it also leads to a vision in which hosts themselves and data centers and things like that, like processes, are relegated to a subordinate role. Ephemeral compute as needed for a world populated by long-lived data. This is wild. Okay, and after all, when you're strung out on a vision like this, you can't help thinking like, what is a computer anyway, man? Like, what is a host? I mean, if computation is the bigger part of computation is just rendezvous, then hosts are just like places and times at which data that is supposed to be combined can affect that combination. Okay, I just want to say this talk is about to go off the rails a little bit. I'm probably going to get excited and talk a little faster. I know I'm already talking fast. The material is going to be a little vaguer than it seemed before, and this is to be expected because in large part, it's research that still needs to happen. Like the questions that I don't have the answers yet for, that's the most exciting stuff. But strap in because it's going to get a little weird for a minute. Okay, this is the coda. Let's look at computation in the large. So there's this computer, I don't know, Alice, and she has a program. So the blue thing is a computer. The boxes are objects in Twizzler. Okay, Alice has some program P, and it's got a thread of control running in it. And then sometimes it has a pointer. So sometimes it accesses data in a data object D. And sometimes the thread of control jumps over into some library code, maybe, and then jumps back. But let's say there comes a time at some point where we reference data, or we attempt to dereference a data object, and that data object just ain't there. It's not on Alice's computer. So what should Alice do? In the current state of the art, Alice would talk to some kind of discovery service maybe and find out that there's this other computer named Bob who happens to have the data. So she asks Bob for the data, they do protocol, blah, blah, blah. But in a more data-centric world, I mean, wouldn't it be nice if we could just transparently handle this as a fault? Like, wouldn't it be cool if, so Alice is like, well, that data ain't there. So process P is suspended. And then with the help of some slightly magical content-based networking that we're working on right now, by the way, we identify that Bob has the data item. And we just kind of fault it over. We figure out a way to route the data item back to Alice. And then we resume the program. And everything's great, right? That was cool. Transparent remote faulting. We've seen things like this before. It's not that disruptive, but it's cool. Now, let's keep turning the crank. Would we throw the data item away right away? Almost certainly not, right? Why? Well, because we'd be discharging some intuition that like, well, keep it around, because if you just use it now, you're probably going to use it again, right? What is that? That's caching. You put a pin in the thing and keep it around. Because as I said, we have this assumption, this heuristic about locality in time. Objects that are accessed are likely to be accessed again soon. But what is it that we're really trying to do when we do caching? What's the thing we're trying to optimize for? It's not about time at all. It's like, I want data that I am gonna compute on to be local before I compute, so that when I reference it, it's fast, right? That's what I want. And caching is just a heuristic that often gets me that. All I really want is for d prime to be there when I use it. Does that make sense? So caching approximates the identity of the objects we want to access using this heuristic of locality and time. And caching has a brother that we're all familiar with too. These are the two hammers of system programming, right? Keep it around for a minute, lasso its neighbors, right? The idea of prefetching is discharging an assumption about locality and space. Hey, if my computation referenced d prime, I should bring over d prime prime too, because d prime prime is adjacent. It's its neighbor. And so there's a good chance it'll get used too. We're discharging an intuition about locality and space, but what are we doing it for? Exactly the same reason we did caching. Because I want data objects that I am gonna reference in the future to be on my machine, please. Thank you very much. So caching and prefetching are the same thing. It's just that prefetching is approximating identity using space. Right? So we bring it over, and in this case, we got lucky because the program references d prime and then d prime prime. We're glad we did that extra speculative work. But if you take a step back and you imagine that you're in a system in which the system, the operating system, understands data identity, then you don't need to do that crap, I don't think. Because after all you wanted was identity. And I can determine all the things that I might ever compute on just by following the data. Just by following the transitive closure of the refers to relation. And this is just the tip of the iceberg. We can keep turning the crank on this, because why did I act like the right thing to do when Alice doesn't have some data is to fault the data in? The data might be really big, right? That's a very agent-centric way to think about the world, as though Alice gives a shit if she gets to be the one doing the compute. Right? If data are the citizens, they don't care, right? Where it happens. So why wouldn't you also consider faulting out the compute to Bob? Because after all, what is the compute? I have a program, which is code, which is in an object, because everything's in an object in Twizzler. And I also have the current state of the computation, like my processor state, contents of my registers, my program counter. That's also in an object, because everything's in an object. That's object S. Presumably those objects are small relative to d prime. Why don't I move them over? Or in fact, as you start to squint your eyes and rub your eyes and look at this, it's like, oh man, affecting rendezvous in a distributed system is really like a global scheduling problem more than anything else. You want to move the data and the computation to wherever it is that you have heterogeneous compute resources that can do the work, right? So the right answer might not be shipping the data to Buenos Aires, shipping the compute to San Francisco. The answer might be affecting a rendezvous somewhere in the middle in Mexico City, because all we care about is the data getting transformed, right? So that's wild. Just total disaggregation, vision of data just floating around the world and acting when it can. Holy shit, you know, like I guess what I'm saying is that the foreign object table carves off a piece of what we used to consider program analysis, the domain of the PL people, points to analysis, and brings it into the purview of the operating system. So now the operating system, as I just showed you, can do a significant number of best effort things because it understands what data means. Now, some of you, particularly those of you who studied consistency, as I have, may be a little bit worried at this time. You may be thinking, wait a minute, like, what if this happened? What if Alice had some data, Bob had some compute, Bob faulted in the data, he used the compute to mutate the data object. So now it has the same name, but its contents are different. It has changed. This is a mutating operation. But around the same time, Alice, who never threw the copy away, computes on D and produces some other divergent replicated copy of the data. Now we have disagreeing copies of D. What do we do? Do we throw one away? What do we do? In some sense, I was cheating because I complained about how processes assume the worst about conflicts, and then you saw me just assuming the very best about conflicts. So this is where this stuff kind of goes off the rail. This is research that still needs to be done, but I want to share where my mind is, and maybe it can start some conversations that you all can help me sort this stuff out. What do we need to concern ourselves with when we think about sharing and the kinds of conflicts that could happen in a massively distributed object-based system? We need to think about a couple different dimensions, right? So one obvious one is, how many people are writing the file, right? If it's a shared library that essentially has 0 writers, we have a trivial problem. If everybody all over the world is constantly trying to access it, it may not be so obvious, but for patterns where there's only 1 writer, you have the intuition. There's lots of really easy built-in best effort system support that we could provide. There's another dimension of interest. I've kind of crammed 2 dimensions into this one, actually, but this idea of hotness. How frequently is the data accessed? Data that's accessed very infrequently is easy to share. But also, is there any sort of, is there any locality of reference in space? Like, is there a small clique of users or a particular physical area where most writes originate? In those special cases, it's very often easy to find a good partitioning, right? So there's all these special cases, like here when we're not all the way at the bottom, here where we're not all the way at the lower left, and so on. And then there's another dimension that's a little bit more esoteric, but that's really interesting to me. And for those of you who know my PhD work, it won't be that surprising, which is this dimension about, like, well, in what ways is the object permitted to change over time? With one extreme being, it can't. It only changes once. It's immutable, which obviously makes sharing easy. Or the object can change in arbitrary ways. Or something in the middle, like the object changes in predictable, progressive, possibly monotonic ways. For example, if my object were representing a set that grows via set union, I would have this property that I could always resolve divergent updates by merging the sets using union. So you all have seen this stuff before, right? CRDTs, that kind of thing. If I knew that my objects were CRDTs, I could aggressively merge them. And by I mean the operating system. Right? So if we lay them all out in the same space, I'll first admit that it's a little bit of a fiction because they're not totally orthogonal, right? The 0 writer case and the never updated case and the immutable case all kind of converge to a singularity over there in the upper right. That's like the trivially easy region. But apart from that fiction, I still think it's very interesting to visualize the space in this way, because we can begin to write out regions that are safe, regions that Twizzler could provide a best effort sharing mechanism automatically without having to have the application solve every problem as an end-to-end concern. So let me, for example, shared libraries are the easy thing all the way in the upper right. An object like a mutex is like the hardest imaginable thing. Like, what if we wanted to create a lock? Well, we would have to put the lock state in an object because everything's in an object. Now, how should we share this object? Should we make copies of it all around the world and create a cache coherency mechanism for it? No, it probably just makes sense to just have one copy of that object, right? So over on the lower left, there's some things that they just shouldn't be shared, goddammit. But let's try to map out this space and see what Twizzler can help with. The first point to make is that this whole region is trivial, right? If data doesn't change, you should share it everywhere, right? If data is only written by one person, you can disseminate it everywhere using whatever mechanism you need to satisfy your recency guarantees. You can use a pub-sub system to disseminate and have multiple copies of the object. So in this whole regime, which is like 2/3 of the total sharing space, Twizzler can provide a built-in sharing mechanism. Obviously, applications could override it, but system support is great when you can get it. OK. As I said, if you happen to know that your object is a conflict-free replicated data type, it has a merge procedure, which is deterministic, associative, and commutative, or if your program logic was written in a language about which you can prove progressive properties of the written objects, like in a language like Bloom, this whole region is trivial to provide system support. We can provide optimistic asynchronous replication because we happen to know if we have a merge graph like this, that if anybody, Carol in Mexico City happens to see these two divergent copies of data item A, and she knows they're the same data item because of identity, and she knows she has a copy of the merge procedure because it has identity, it's just an object. She can take them to their union, throw them away, and then disseminate D prime prime prime, because any other computer seeing those same inputs would reach the same deterministic conclusion. So that leaves only a really small region of the possible space of different ways your application written on this operating system might want to share data, for which there isn't a slam dunk built-in solution. And should that be so surprising? Objects that are written by many people, uniformly by anyone in the world, all the time, and they can change in arbitrary ways. Like, there be dragons, right? There be a cap theorem, right? There be Paxos and Raft, and like we've solved problems in that region. It's just they all look a little bit different. So I think like worrying, oh yeah, I should point out, if I wasn't building an operating system, if what I was building was like an infrastructure component like Corfu, it would be tempting to say, you just can't do that stuff. We provide support for this region, and don't worry, that's most of the stuff you want to write. Don't go there. If I were writing a language, as we did with Bloom, I would simply not allow you, I would make the language not expressive enough to write programs in that region. But unfortunately, I'm not building an infrastructure or a language. I'm building a general purpose OS that needs, I'm not building it, Daniel's building it, that needs to support any possible application, which means we can't black out the region of Dragon. But nevertheless, Twitter's explicit notion of identity facilitates built-in best effort system support for most of the space. Worrying about the fact that distributed Twizzler may not have a slam dunk strategy for that region is probably dwelling on the negative. I'd prefer to celebrate what we can do in the short term and then to mint 2 or 3 PhDs exploring that stuff in the lower left-hand corner. I think like the picture's pretty good, right? Like this is nice. So this is pretty much the end of the talk, okay? And in case you fell asleep, I want you to remember 3 really important things. The first is that in the limit, the lifetime of data goes to infinity, and the lifetime of a process goes to instantaneous, which means we should center our systems around information and then center our programming models around information. This was always the right model of computation, but now is the right time because Byte-Addressable MVM is coming, and we are going to either use it or lose it. Finally, follow the data. Twizzler's object model with its invariant and explicit references enables rich built-in system support for the most important thing that systems, and importantly distributed systems, do, which is to share information. Applications, the stuff we write, have always followed the data. With the help of Twizzler, now the operating system can follow the data as well. Let me just close with a quick thought. What are y'all doing right now? How do you want to spend the next 5 years? It seems to me you have 2 options, right? You could play it safe, hang on to your industry job, or you could do something really radical. You could go blue sky. I know a place with really blue skies. I know that it's a profound risk. Consider taking a chance with us. I know there's danger there. I've been there. I've seen the images firsthand. Some people call Santa Cruz the University of California's most striking campus. Why do you think you see so many images like this out of Santa Cruz? Well, it is a really photogenic place. But more importantly, at Santa Cruz, we fight like hell for what we think is right, and we don't stop. Consider coming and fighting with us. I promise to have your back. We all will. I want to thank all of you, but especially Daniel Bittman, who built Twizzler. That's it. Thanks.
Oh man, I mean, operating systems plus a really cool politics in a really nice place. It's like the dream come true. So if I was from the computer science field, which I'm not, I'm coming from the humanistic field, I'd be packing my bags. But I think I'm really glad this was our last talk for the BuzzConf because it allowed for more time to develop the idea, which I think is so amazing and so interesting. We have a few questions, but first of all, I would like to invite everyone to Twizzler.io, where I think you can download version 0.2. Is that right?
I'm not sure what version it's at right now, but you can download the documentation and the OS. You're not going to have a lot of fun trying to actually compile it for bare metal right now. So I would encourage you to try to run it in an emulator like QEMU.
Okay, and so one question from our audience, which I think links to the last part of your talk. Niv says, address space is theoretically collision-free, even with distributed computing, but doesn't it need a translation of some sort, depending on the nature of the network, like IP?
Oh, it's a wonderful question, and it's one that we've been thinking about aggressively lately, because now that we have the operating system, we're beginning, like we just pushed our first Ethernet frames over the network this week. So the networking story is very much in its infancy. So I want to make a point that the 128-bit object ID space is big enough that if everybody in the universe picks random numbers, the likelihood of collision is really small. So within that ID space, it is sufficiently large. That is not to say that 128-bit flat ID space is going to be sufficient to support hierarchical routing. So initial prototypes of distributed Twizzler are likely to be rack scale, row scale, data center scale. And in those cases, it's probably going to be OK to use content-based networking over a flat address space where, like what we're imagining right now is you don't have IP addresses. Literally, what you ask for is the object ID, and you are routed to it, or it is routed to you. So it's object IDs rather than IP addresses. If we went to the WAN, this would not scale. Switches couldn't hold that state, right? A router can't hold all the state of the internet. It has to. You have to be able to route to a router, and and then it routes you further, right? So we would probably need to, for the WAN, come up with some kind of overlay network that was either hierarchically structured the way that IP is, or that was, like a consistent hashing ring kind of thing. Like we're going to cross that bridge when we come to it, but we are aware that we're going to need to overlay something over the flat namespace to route across large geographic distances. Thank you for the question.
Okay, another question. How would you compare Twizzler to Ethereum?
Ethereum, the blockchain thing?
I think so,
well,
yeah.
I think like, I think, Twizzler's a general purpose operating system, and Ethereum is not even exactly an infrastructure, it's an application. But I think it might be an interesting question. Let's say that you wanted Twizzler to be the substrate for just highly distributed blockchain. What would be easy? What would be hard? Like, what would explicit identity that you get from Twizzler, what advantages might that have in a Byzantine fault-tolerant world? Honestly, I don't feel totally prepared for the question, but I'd like to ruminate on it some more. Like, yeah, it's a good question. I think like on the surface, Twizzler will support every application, including Ethereum. But I'd like to be able to say, maybe there's some way it could support Ethereum better than Linux does. I just don't know off the top of my head.
Okay, great. So a third question, which is the biggest weakness or obstacle or monster that Twizzler faces?
Oh my God, can I say more than one? So I think that it depends what you mean by obstacle. But in the academic world, right, it's publish or perish. And I think publishing Twizzler was profoundly hard because nobody wants to hear about a new operating system, right? You send your thing to a conference and they're like, why do we need a new operating system? Why can't we just use PMDK? Why can't we do something incremental? It's extremely hard to sell a somewhat conservative community on a blue sky idea. So I feel like that was the biggest obstacle, was getting people to listen. Now that we have the ATC publication, I think we've bought ourselves a little bit of credibility and we can keep turning the crank on this wild idea. But I think that was really hard. I think the other thing that's really hard is human power. You know, like an operating, you know, when they developed BSD at Berkeley, that was like 10 years and 20 PhD students built that thing. We just have this one boy writing this OS and he's going to graduate soon. And so like finding, like there's so much work to do when you're building something so big. And so finding like people power is probably almost as big a hurdle now that we have a mandate. You know, when we got the paper, it's like, okay, this is for real. We're actually going to build this thing. So, oh crap, we need 10 people.
Sure. Another question from our audience. What is the emergent value for society of this new paradigm? I mean, what will this translate to? Speed, cost, security, simplicity? What advantages can you sell society on?
Yeah, that's a great question, and it's one that academics and industry people should be forced to answer, put on the spot and forced to answer more often. I think the principal benefits of the model are radical simplicity in the programming model more than anything else. So I think, as I showed you when you looked at the key value store, something happened with that key value store that has never happened to me with system design before, which is that I could be lazy and not think of the whole picture and incrementally develop things and then think of things I wanted later, like access control and secondary indexes, and lay them on. So it's a programming model that's not only easy to use and natural to use, but there's some evidence that it makes it easier for systems to grow. Right? So it's not just easy to write that 250-line KVS. When you want to go write a much more complicated KVS, you have a much better modicum of reuse of the old code. So I think the principal benefits are programmer productivity. And then think about that cycle that I was showing you. In Twizzler, most of the steps in the cycle, you simply don't need to do, because it's not your job to be the ferryman between volatile and persistent. So all those programmer cycles that people used to spend on data movement, they can spend on innovation. And the hope is that this will lead to a proliferation of new algorithms and data structures, maybe new algorithms and data structures that are particularly suited to BNVM, which has some different characteristics. So there's a bunch of new work to be done there too. I do think that Twizzler has some advantages in terms of security, particularly in the distributed setting too. But I would prefer not to talk too much about them because I don't understand Twizzler's security model as well as Daniel does.
Okay. I think simplicity is a great added value in a world where systems are increasingly complex. So that's a lot. And a question for the future, perhaps. You said you can envision some applications of the operating system. Are you currently trying to think about that and speaking to potential sectors that can implement it, or are you still in the design phase and not thinking about application so much?
It's a really great question, right? So obviously we want to have a full stack story, and the story's not really going to be compelling until we do, until you have until you're like running Jupyter notebooks on this, and you're running Ruby on it, and you're running Rails on it, some real like applications at the top of the stack. The thing that's unfortunate is that most of my colleagues, we are infrastructure people. So like my whole life, I've been doing back-end stuff. So of course, like my first thing is like, oh, I want to go implement memcached on top of Twizzler. And then it's kind of like, that sounds cool, but Memcached isn't an application, right? Memcached is a piece of infrastructure. Like, are you going to build Twizzler on top of it, or rather Twitter on top of it? And I say, I don't know how the hell to build Twitter. I can't do JavaScript. So we probably need to get, again, it's a human power thing. We need some application programmers. So Daniel Bittman, a master C programmer, being an application programmer on Twizzler, building an application in C and saying C wasn't that easy, is not as compelling of a story as if like a Rails developer was able to do something much more easily than they could have done before in the new thing. So I think we absolutely need to build up to apps. It probably won't be me and Daniel who are doing it, so we need to enlist some front-end programmers. And we probably will crawl before we run. We probably will build some infrastructure, some storage systems, some caches, and then on top of them, build that third tier. So it's absolutely necessary, you're right. It's not the next thing, both because we need to work our way up and because we don't have the expertise in-house to write like real applications.
I don't know if you have mentioned this already, but what is the license of the operating system?
It's MIT license. So it's a permissive open source license. I think you'll find that a lot of times, especially these days, because we do rely on funding from companies, all academics want their stuff to be public domain, right? Their papers. But we're a little bit gun shy about GPL, because GPL a lot of the time will be a poison pill for potential collaborators. So academics tend to license their stuff. No, I think it's BSD license. Academics tend to either do MIT or BSD. I can never really tell the difference, but they tend to be like the permissive open source licenses.
Okay. Yes, I think one of the key aspects is building a community around it. And I was talking to one of the creators of Julia the other day in a talk here at BuzzConf, and they almost let the community decide where they want to take the language now, because they got a lot of smart people on board. And I think it's key to build that, around, get people excited, which we hope BuzzConf can contribute to get people excited about Twizzler, and not only send smart people to the campus there in California, but also build a community around the world that can contribute their free time and their minds and think about these problems and start conversations. So I was wondering, is there any place where you hold conversations publicly about Twizzler, where, I don't know, Niv, who asked all these profound questions, can talk to you and continue thinking about this?
Thank you for your question. There should be. Why don't we create a Slack channel for Twizzler?
Yes, let's do that.
We'll do that. We'll do that right away. Daniel will be delighted.
Great. So I want to send a big hi to Daniel, who is in spirit here with us. And thank you, Alvaro, Peter Alvaro, and thank you, Daniel, too. And thank you all who are building Twizzler. I don't know if there's another question from our audience. They're saying it's a fantastic presentation. And I wanted to mention that people were saying their minds were melting. Their brains were melting, and then you said this talk is now going off the rails. It's a really blue sky idea, which I think it's going to leave some of us thinking.
I want to say one other thing, which is that I did my undergrad in literature, and then I applied to Berkeley for CS. So if you really think you're interested, don't sell yourself short. I mean, sometimes humanity background it fits very well with this kind of work. I mean, especially, crazy idea stuff, right?
Okay, I need to study a lot more about operating systems. I know very little, but yeah, I think it's really exciting. So I hope I can contribute in some way. I mean, at the very least. So thank you a lot, Alvaro, Peter Alvaro. I'm sorry, Alvaro is the first name here.
I know.
Thank you, Peter, so much. Sure, I'm going to try to contribute as much as you think I can. And so it was great having you here. We are going to keep this talk on the YouTube channel of the BuzzConf for anyone who wants to see it later, or if you want to share it with more people.
Great.
So thank you for being our keynote speaker and closing this amazing event.
Thank you so much for having me. I had a great time.
Okay, and defend the kernel and every shitty thing out there. And thank you for standing up for the good things there in the United States. And we are with you on all of this.
Thank you. It means a lot.
Okay, bye-bye. Oh, there's a standing invitation to come to Buenos Aires next year or whenever they allow us to.
I promise.
Okay.
The very first chance I get.
Okay, see you soon then.
See you
Bye.
soon. Thank you so much.